Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
Good evening. I'm Yvonne, Staff for Science for the Public. Welcome to Contemporary Science Issues and Innovations. This evening we have with us two distinguished mathematicians, both from the Massachusetts Institute of Technology. Our guests are Gigliola Staffilani, the Abby Rockefeller Mose Professor of Mathematics, and Tomasz Mrowka, the Singer Professor of Mathematics, both of MIT. And their respective lists of distinctions are so lengthy that we must abbreviate it here and refer you to the Science for the Public website page for this event for more details. Dr. Staffilani received her PhD from the University of Chicago. Before joining the mathematics department at MIT, she was a faculty member at Stanford and at Brown and at Princeton. She's received numerous prestigious awards and fellowships, including one at the local Radcliffe Institute for Advanced Studies, and she's the editor of two professional journals. Her research is concerned mainly with dispersive partial differential equations, used especially in physics to describe wave phenomena. Dr. Mrowka received his PhD from UC Berkeley, and before joining the MIT Mathematics Department, he was a faculty member of Stanford and Caltech. Professor Mrowka's research focus is differential geometry and gauge theory, both areas especially important in high-energy physics. He chairs the Pure Mathematics Committee at MIT and has received numerous prestigious fellowships and awards, among them the Veblen Prize in Geometry and the Joseph Doob Prize, both shared with Peter Kronheimer. Professor Mrowka is a fellow of the American Academy of Arts and Sciences. Tonight, we'll be talking about the importance of math in everyday life, the critical role of mathematics in modern science and computation, some types of mathematics that we're not familiar with necessarily, and the very interesting work of our two guests. It is a very great honor to welcome Professors Staffilani and Mrowka. And let's start with just the significance of math. As you are aware, we have a disease called math anxiety in the United States, now demonstrated to be genetic or something or other. You both have ancestry from countries that are famous for mathematicians. They generate them all over the place, Poland and Italy respectively. What is our problem? Do you see our problem, and do you think it's a real one?
Go ahead. Well, I guess Tom was educated in the United States, although he had parents from Poland. But I lived in Italy until my undergraduate studies, and I left to come here to the United States for a PhD. I think one main difference that I found between my education and education of women in the United States is that in Italy I never heard that women couldn't do math because they were women.
Yes.
So actually quite the contrary. Throughout my high school and also middle school, girls were considered to be better at math because they were more diligent, they were more neat, they could write much better, and so it was very common to see girls to be the top performer
I
in the
see.
class.
So even you might say a more traditional culture, nevertheless, this was not a hang-up.
Yes.
I should point out that our problem is pervasive. It's both genders, it's all economic, socioeconomic classes. And you may know that there was an article recently in the Times and in a couple of other places, but an op-ed in the Times, do we need algebra? Couldn't we get rid of it? Because everybody's flunking it. Could we get rid of it? It is upsetting the self-esteem, et cetera, of all the students. May I have your opinion there? Is it important?
Absolutely. And I actually think that in order to have children and young adults to perform better and gain self-esteem, I think one has to make math harder than it is. I mean, you know, of course I like it because this is my profession, but I don't think that in order to make everybody happy, the standards need to be lowered. This is ridiculous.
All right.
Actually.
It's maybe backfiring or something.
Totally. I mean,
yes.
I was just hearing the other day how, you know, there are jobs in the United States. The problem is that there are not people that have backgrounds.
This is very true.
And the jobs that are available are more based on science and mathematics, and people are not trained for it.
That's absolutely
what we are
true.
doing is making people less suitable.
Exactly, and
there.
maybe lowering confidence or something
so.
as we go. In terms of this training for like just being citizens, what do you think? I mean, what do you need to know as a citizen? Just basic stuff for math.
Well, I think these days, knowing statistics, knowing how to read graphs, knowing, you know, just simply how to reason, you know, take some set of thoughts, put them together coherently, and see what the consequences are. And we see today in the political discourse in the presidential campaign is abysmally low.
Yes.
And, you know, we have serious problems, and the solutions aren't yelling at each other. The solutions are to figure out, you know, what are the best methods to solve the problems.
Right.
And we need to.
I'd like to pursue that just a little bit more. I think in another place, correspondence or something, you mentioned that math teaches you logical thinking, and another one is the abstraction, how to deal with abstractions or how to generalize. One of the things that is very noticeable perhaps here in this culture is a tendency to be very focused on oneself, one's experience. How do I feel about this? Actually, the business of, I don't know, little bugs on the nation's highway or something like this. So that we're being pushed to a very trivial level perhaps. But in your mind, how does math help you transcend this very personal level? Does it?
Well, it does for us.
Clever answer there. Evasive, but clever.
Well, it's hard. You know, we both teach at MIT, so the students there, they're fantastic at math. In fact, they're better, I think, than they were even certainly when I was a student. And so, you know, there are students who are being trained well, and that's great. But obviously, there are a lot of people who just have no, you know, understanding how to deal with the complicated things that happen in society these days.
Right. So, and perhaps to be able to generalize and think logically, think through things, and yet everything, especially in a computer culture, it depends on being able to make logical kinds of analyses, perhaps. So
and
it's
also,
interesting.
We live in a very complex society, and I think it is very important that people know how to organize themselves and how to dedicate a certain amount of time to a certain amount of tasks. And on this, I guess it is important to understand patterns and how to reach certain goal by allocating the right resources to each one of those things. So it is this idea of being comfortable with abstraction and recognizing how to connect problems and say, well, these two problems are basically the same. I know how to solve one, I know how to solve the other one. It just gives also a lot of confidence.
Yes, that sounds like a very reasonable thing, and that business of seeing patterns and so on is an important thing in being able to solve problems just generally at any level, perhaps. Well, in any case, I hope that you will solve all our problems and help encourage young people to study math. It seems like it's the wrong way to go to say, let's just drop the thing. We drop geography, grammar, I don't know what else. So what's left, then maybe we should have this back, and especially in a global world. We have a global community now, and we have to solve problems in a radically different way, and a lot of it has to do with science.
And certainly our competitors are not
No, they're not shy. That's right. They're not dropping out of it at all. Very rigorous attention to mathematics in other leading cultures, all other leading cultures. I'd like now to ask about the kinds of mathematics. For most of us, it stopped somewhere back there in high school, some vague place, calculus, stuff like that, and Euclidean geometry or something or other. But there are lots of areas of mathematics. So could you give us a little menu of the kinds of things? We're going to talk later about your particular things in more detail, but by all means mention those too.
Maybe I'm going to start and Tom will add to it. So I think there are in general three main areas that nowadays I guess are really very much intertwined. So there is an area which is more dedicated to algebra, and I guess I would put there also number theory and algebra geometry, algebra topology, and all of that. Then there is geometry, and of course there is a connection between these two. And then there is more the analytic side. So number theory, it's, as the word says, the study of numbers and the patterns that connects these numbers. Geometry is more the study of the shapes, and of course all this, it's, I mean, there is what you can think that you understand, like everything in 3 dimensions, and even there are complicated questions that are not resolved yet, and you can definitely talk more about that. And then there is the more analytic side, which is deals a lot with phenomena in nature that connects space and time, and then there are of course, when you study a problem, especially a problem which has not been resolved yet in either one of these areas, if you know the other ones, you have a better chance of solving. So the emphasis that we put in our graduate students is that when they come there the first year, they absolutely have to take classes in all these areas, because they will have many more tools later on when they will specialize in one of them.
All right.
Tom can
add
on it more.
Well, so another area that we haven't mentioned is there's mathematical logic. That's a very important discipline. It has close impact in computer science, for example, in testing whether a program actually does what it's supposed to do, there's so my specialty is geometry, and geometry arises in almost any problem that you start to think about. If you imagine just how a robot has to move its arm, then you need to think about what is the what physicists and mathematicians call the configuration space. What is the space, the set of all positions, and that space can be very complicated, not just like our 3-dimensional space. It can have many different dimensions. If there are many different moving parts, they each have a way of, can be in different positions. There's, statistics, we've mentioned that. Statistics has a lot of important applications. I mean, on the breadth of science in understanding how DNA works, for
Yes,
example.
absolutely. It's I was going to say it's very important right now. And yes. Right. So it covers a lot of ground. I think most of us who are not trained in it sort of think of math as out there somewhere. It's very abstract and it's out there. And it's not permeating everything, but in fact, it's quite the opposite. And if we wanted to understand the world, we have to look at math. But there are many ways, many routes apparently through mathematics, and different types of mathematics could take you into different directions. Is that the case? I'd like to just say something, ask something about geometry before we leave this and talk about mathematics and science, particularly today. But in a recent article in Scientific American, there is one of these grand unification theories things by, I think it's Lisi, I think of him as the surfer, but he's a famous mathematician. And it's an incredible geometric design, and it includes everything. So I wanted to ask, well, if you get to the really bottom of everything, are you looking at a geometry? Will that tell us everything?
Well, geometers think so.
There we are. A truthful answer, if there ever was one. Yes.
I mean, in fact, Lisi's theory is extremely controversial.
Yes, so I understand, and he is. It is true, isn't it, that just because you have a good idea, it isn't necessarily accepted at the time, although it may be true, or it may not be true, although it is accepted at the time. So you could have it in any direction, but I am struck again and again, just as a lay person, at how much geometry is out there. It's just in everything. So, and the rest of it is these other very interesting ways of touching reality. So I'd like to get into that now. So again, now it seems like there's a great leap in where science suddenly, from late 19th century, but certainly the 20th, makes just a very huge developments in, say, 100 years or something like that. And in tandem with this, is this correct, new mathematics as well to try to get at this. Could you explain, first of all, just this, what seems from the outside a co-evolution, and can you give us any examples?
Mathematics and physics have, evolved together from the beginning.
Joined at the hip.
Newton, after all, if you ask a mathematician, he was a mathematician. You ask a physicist, he was a physicist. Right? And since then, the development of quantum mechanics is a fantastic example where, Heisenberg and Niels Bohr used the idea of using matrices to describe physical reality instead of using the motion of a particle to describe physical reality.
Yeah.
And more recently, physicists have used ever more sophisticated mathematics in trying to understand. String theory is a very popular part of high energy physics these days, and the kind of mathematics that they use very sophisticated algebraic geometry, they use very sophisticated differential geometry, even number theory sometimes, and and sometimes the physicists make predictions using their tools that the mathematicians had no idea about, and other times the mathematicians have developed the tools that are exactly the ones that the physicists need to move forward, and that's been such a long-standing tradition. There's this fantastic article by Eugene Wigner, which is the unreasonable effectiveness of mathematics in the physical sciences. So,
I think also another example of this is number theory and computer science and computers, right? So in particular in number theory, like I said, people love to look at the relationship between numbers, which one could think is beautiful, but basically useless, until people found out that that kind of relationship that you find with numbers could be used in order to encrypt things that you want to keep secret, right? So codes and all that. So I think after World War II or during World War II, that was when people started using these special keys that come from numbers.
And it all came from number theory.
Yeah, so that was there somehow, and people thought that was just a beautiful theory, but some clever person actually used that tool. So that was an example in which some abstract mathematics was used, just like maybe the geometry of Minkowski was used in order to express general relativity. At the same time, mathematicians try to sometimes justify their job by saying, well, you see, you can use this to do that, and vice versa. Something totally abstract can be used for reality.
That seemed to everybody that it was far out somehow, and with
totally
no
practical
value,
yes.
or I don't mean practical in the
but
everyday sense,
application.
but an application. And then, in fact,
yeah.
it did turn out like that. On that also, it's a very interesting thing about mathematics that I forget who used this term, but mathematics does a lot of prediscovery. Mm-hmm. So there'll be something in an equation the mathematician yes. didn't expect, couldn't explain, and then when it is yes. coughed out, then it might take years yes. before you can prove that experimentally. So antiparticle, quite a few things, evidently.
Exactly.
Please explain that to us. What is the magic there?
Well, I think part of the thing is that mathematicians are very much driven by kind of an internal aesthetics. You yes. try and find the yes. patterns that are the most, the simplest patterns to explain the most complicated possible things. And I think that's, so good mathematicians are good at it.
Yeah.
And they, it just happens that, we find the right thing.
Yes.
Often.
So this is, I'm going to ask you to sort of step us through this too. Yeah. But so you would make an equation.
So for example, like just today I went to a talk, and the speaker was explaining how there was a problem that came from nature. It was a optimal transport kind of situation. And you can write, and then you translate this question by using functions and variables and all of that. We know how to do this very well. And then you see an equation. And then you ask your question, okay, first of all, does the equation have a solution? Mm-hmm. Because if it doesn't have a solution, it's not a very good way to translate a phenomenon, right? And then you start doing your mathematics following very strict logic that puts everybody in agreement. And then you say, well, if this quantity, like a certain function, is positive, then mm-hmm. I can say that there is a solution. At that moment, it's a purely abstract kind of condition. Mm-hmm. I mean, it's a totally mathematical mm-hmm. condition, and you might write a perfectly acceptable and probably great theorem with that condition. But then you might step back and say, what does this mean for the object that I'm trying to describe? And you realize that that particular mathematical equation basically is telling you, for example, that on the surface of the ocean there are no waves that are going to break, mm-hmm. and that's a singularity for us. Mm-hmm. So assuming that quantity is positive means that you are assuming that the wave will never break. Mm-hmm. So that might not be there at the beginning, but you find it, and then you wonder, what does that mean? And you go back, and that is an expression of a certain phenomena. And we keep doing that a lot.
That is really fascinating that it comes up just
like
out
that.
of
Mm-hmm.
your thinking, your
yes.
imagining, and there it is. And you can pretty much tell that is something valid really there.
Well, that's exactly the point. I mean, sometimes we make assumptions mathematically because we don't know how to do it otherwise. And yes. these assumptions are too strong, meaning they don't really have a physical meaning. You realize that it's too much. You should try to prove the theorem without that assumption, because that's much more physical and it's much more beautiful. So it's also a way to decide, to gauge how strong is a result, in a sense.
You mentioned theorem, and I'd just like to inject here that I think we have a fair amount of confusion, definitely between theory and hypothesis. So you hear statements like, I don't want to get off the track, but evolution is just a theory,
Yes.
you know, or something. More recently, somebody said it's time to stop calling the standard model a model. It's so good now. It's been demonstrated over and over again. There's so much proof. It should be called a theory of reality. I think, uh-oh, we're in trouble. And then you mentioned theorem. And I wonder if you would do this for us, just straighten us out on these terms, okay, if you will. When you get a theory and you have a theorem like Fermat's last and the new ABC one and stuff.
My point of view on this is that in mathematics, among mathematicians, there is no confusion at all.
I understand. It's us.
So, I mean, a theorem is like you have some hypothesis, and then there is a statement that you wanted to prove that it's a consequence of those hypotheses. And once you find a proof, the theorem is proved. You can also make a conjecture. You just say, this could be true. And maybe people will prove that that conjecture is true for many examples, but we don't call that a theory.
Okay.
I mean, we don't say that it's proved unless you come up with a complete logical sequence of statements that proves without, you know, just that statement then is still a conjecture. For things like evolution and other kind of theory, well, they might be, mathematically, they might make perfect sense. They're proved for us.
Exactly.
But whether this theory is actually applicable to our world, that probably takes some experiments.
I understand.
Matching.
And some things are out of reach. So when you get to like the string or
Right,
something
right,
that's
exactly.
really out
Yeah,
of reach,
yeah.
but standard model, they managed to do a great deal with, so it was more in line with.
I mean, one thing that might help clarify that is if you look at, you know, if you're trying to learn a particular science, then typically what you need to learn, you know, you certainly had to learn some of the historical stuff in the science, but really what you need to learn is stuff that's happened in, you know, the past 10 years, something like that. Whereas in mathematics, you know, you can look at papers that were written 200 years ago, and they, you know, I mean, people have learned to write somewhat better, but, you know, they are readable. There's whatever they said was true was a theorem, it's still a theorem. So it's still, you know, so mathematics is unique among the sciences in that way that, you know, what was true, it's still true. You know, maybe the assumptions that you, maybe it doesn't apply to your situation because they didn't make the assumptions that you want to make, but it's still.
You can generalize it, but still that fact was.
Right. Thank you for that. We just needed to get these things a little bit straightened out. I know you don't have a problem. It's the rest of us in the world who do. Before we leave this, I'd like to ask about, it's a common phenomenon in science is that somebody comes out with a brilliant insight, a new idea, and everybody says that is total nonsense, and the poor soul is humiliated forever. And I don't know how often this happens in mathematics, but I was thinking of Boltzmann. Not sure whether Dirac got kicked out of the room, you know, when he came up with this idea of an antiparticle. Mandelbrot definitely was ridiculed when he came up with fractal geometry, which had been sort of around, I understand. So do you tell me that that is an infrequent thing?
I think in mathematics it's quite infrequent. I mean, you know, part of it depends on if it's really in pure mathematics. I think it's very infrequent because, you know, the test is, you know, did you really prove your ideas, or are they in a very precise sense, do they, maybe they're conjectures, but they need to make progress in the field in a well-defined way. Mandelbrot is, you know, he was more of an applied mathematician. He wanted to take these ideas that were around before. That notion is fractional dimension.
Right.
Was an old idea, which he picked up and thought that it actually had applications to the real world. And that's, that's where the friction was. So in a math department, people wouldn't necessarily appreciate what he's doing because maybe it's not fantastic mathematics. It might be fantastic science.
I see. Yes.
So maybe.
Oh, but that's a different thing. Yes.
No, but
yes, right.
it's
right. I understand. It's outside the fold of
maybe
what
he
you
belonged
do.
to the physics department.
Exactly. Well, that's cheery news because in so many areas of science, people really do suffer. When they come out with something quite bold, and so I wondered, when they came out with string theory, they haven't seemed to have gotten into a lot of trouble yet. But you've got Ed Witten there, and he's just so prestigious that I guess you don't ridicule him.
Well, the mathematics behind it, he's a mathematician.
Exactly.
The mathematics, as far as I understand, it's quite.
Okay, so the mathematics is impressive, but it's something that doesn't lend itself to experiment.
As far as physics goes, we cannot comment. But
Right.
certainly the mathematics, among mathematicians, is very, one of the top.
So you'd have sort of confidence in it if it could, it would be certainly worth pursuing if you could, if there were a practical way to experiment. You'd say, looks good.
I don't know the physics behind
Right, I
it.
understand.
From the mathematics
But the
point
math
of view,
is
I can
gorgeous.
accept any theory they give it to me as long as it's logically proved and that's beautiful.
Yes.
It has beautiful mathematics. Now, whether these theories reflect the reality we live in, I'm not a physicist, I don't know.
Okay, very careful there. All right. All right.
You learned that as a mathematician.
Yes, that's right. Really cautious, really cautious. It reminds me of your physician. This is
exactly.
Yes, right. But that's understandable. It's the way to go in any case. Do you expect in mathematics any big leaps in the future? Do you see any directions here? Can you give us some?
Oh, I'm sure there will be.
Really?
There will be. There has been.
Yes, I understand. Do you think
We'll never stop.
Yes, I understand that, but I mean, I'm thinking of in science and across the board in the last even 50 years,
Yes.
the leaps have been enormous and they're accelerating. That is, we keep making these jumps more frequently. Yes. And so you feel like everything is opening up all of a sudden. There's so much to investigate. Do you feel this way in mathematics?
I think that, first of all, we already seen in the last maybe 10, 20 years that the proof of two incredible, important problems, right? The Fermat theorem, the Poincare conjecture. These problems have been open for a very long time. There are a lot more conjectures up there that need to be proved, and I'm sure that will happen in the next, many years. But what I think is making a big difference now compared to before is that people communicate a lot more. We know right away, even before the paper is published, even before the paper is actually. The manuscript is available, from people posting slides of their talks. You know what they're talking about. So these ideas are available.
Exactly. And worldwide,
Worldwide,
which makes a big difference, doesn't it? From old paper journals and things. That's really a really important point, as a matter of fact.
Before, people would write a letter that would take months to get.
Exactly.
And then, now if I think about having to work like that, I will go crazy because I need to know right away whether something is known or not known, or what's known.
That's very interesting. I think you do maintain this kind of a thing, don't you, with, I don't know, with mathematicians and probably in specific fields. And I know that it's true in the sciences too. You mentioned these theorems that have lately been proven, and just for your benefit, apparently, this new thing, this theorem that I've never heard of, certainly, but who am I? The ABC theorem has evidently been proven, and there is a 500-page proof. But this is something that made the New York Times just this week. So I was dying to ask you, what is this? You know, we've heard of the other ones, and that's an amazing thing.
So the ABC conjecture is a generalization of Fermat's theorem.
I see.
It's a theorem in number theory.
Okay.
And it, Fermat's theorem asks if you can solve the equation x to the n plus y to the n equals z to the n. So if you take, when can the powers of two numbers equal power of the same order of another number? So, we can do that with squares. For example, 3 squared plus 4 squared is equal to 5 squared. 9 plus 16 is 25. But you can't solve there's no solution in integers of, where you take like 3 cubed plus 7 cubed will never be, 8 cubed, say. And the ABC conjecture is a conjecture that asks, so that you can think that what's important about that question is maybe it's because each of those, when you take a power of a number, each of them has lots of factors, the number that you raise to that power. So the ABC conjecture is a conjecture that asks, if you have three numbers, a, b, and c, you want to solve the equation a plus b equals c, and you want each of them to have lots of factors, then you shouldn't be able to solve it, and there's a very precise estimate about how badly you should be off when you try to solve that equation. And so there's this Japanese mathematician, Shin Mochizuki, who's claiming a proof. It'll be quite a while, I think, before.
That's what they say. Just
it's
proofreading the proof is going to take a while.
He's also, he's developed a lot of interesting ideas to try and attack the problem. So it'll take people a long time to digest it. Just as it took maybe two years for people to check the proof of the Poincare conjecture really carefully. Weil's proof of Fermat's theorem actually had a flaw, which was discovered, and then it took 2 years to get fixed up. So we'll see.
But it's an amazing thing that people are able to do that, right?
Sure,
That's a huge accomplishment, and you say that it's suddenly everybody's doing it, more of it.
There is a lot of stuff going
on.
And to me, even more interesting is that usually these proofs are not like a simple proof of that particular problem. Usually it's just a whole generation of new ideas, and then it will be used to prove all sorts of different things. So they are never just that paper. It's generating a whole new mathematics.
It's amazing, isn't it? It's sort of like a little genetic thing out there. A new organism
is
out there every time you turn around. Yes, yes. Now, though, I'd like to turn to your respective fields, and you do very exciting things. Part of it's like with motion and things like this, and I hope you can translate it for us out here in the other world.
Maybe I start. So I work on partial differential equations, and these are equations that involve unknowns that are often functions that depend on positions and on time, or maybe on velocity. So they clearly come from physics, basically. And I'm not, like I said before, I'm not a physicist, so I'm not the one who comes up with equations. But these equations are nonlinear, which makes them very complicated, so complicated that it's often impossible to find the solutions that you can write down. So when you cannot write down a solution, hence observe it and try to understand from the solutions properties of the phenomenon that it represents, then you have to analyze mathematically. So you don't know what the solution is, but you can gather from certain logic process what the properties are. So this process of understanding and studying mathematically the equation to then get properties of the phenomenon, in my case would be waves, requires a lot of chopping out. So you have to chopping out, up, yes, chopping up. So you have to look sort of building blocks of these objects. In fact, here it comes a lot. If people know about Fourier transform, that's really the one of the tools I'm using. So Fourier transform says that any signal, basically complicated signal, you can interpret it as the sum of signals that are sine and cosine. Probably everybody knows about that. So you can build them up by putting together a bunch of these sine and cosines. So what I do is using the building blocks and understanding, thanks to the dynamics of the equation that I'm studying, how they interact with each other. And this interaction, if it's studied well in the appropriate way, will give me or predict a certain behavior of the equation, of the solution of the equation. So, for example, people would like very much to understand how freak waves come about.
Yes.
Okay, so how tsunami come about. And it's a very complex problem. We can only see, well, we can only understand a little bit of it. But it's very interesting because often, for example, these freak waves come out of nowhere. Evidently. So it's clearly some kind of singularity, but it's a singularity that is generated by small things all over the place. And where and how, what causes it, it's unknown. Even mathematically, we expect, we try to simplify the phenomenon and try to understand some of these parts, but it's complicated.
It's very interesting. You wouldn't think from the outside, usually, that mathematicians would look at this, at waves, for instance, and things you've mentioned, like I think it's a Bohr, where the particular gravity of the sun and they cause this tremendous force of tidal force. And then you mentioned the freak waves and so on. But we think of these in terms of physics, but not mathematics. But there again.
Right. So, for example, one of the, for me in particular, one interesting part of what I do is, like, there are people who use numerics, so they use computers, programs to generate objects. The problem is that in doing that, you make errors. There is a certain error that you have to control. So what is not clear is whether the phenomena that you see numerically, it's actually the phenomena that is due to the object you're studying, or if it's generated by the error that you're making. So mathematics tells you that no, that's really what you're studying, or that is really an error that comes because you're just approximating not in the right way. So, and we go kind of, together. Like I get sort of ideas from what they look at, and they use my theory to say this is really what it is.
So they really are complementary in a very important way. Very interesting, and thank you. Now, Tom.
So the kind of mathematics I do is a mix of it uses partial differential equations. I study the partial differential equations that arise in high-energy physics. I study the Yang-Mills equations. Those are the equations that physicists believe govern quarks. And it turns out that those equations and their friends, you can use them to address purely mathematical questions. So one of the things that I like to study these days is knots. So if you have, so just imagine a loop of close string in 3 space, but you are allowed to knot it up. Then you can study equations like the Yang-Mills equations that are able to, by studying properties of solutions to the equations, where if you imagine the knot as representing, if you have a current in a wire, then that the current in the wire induces a magnetic field, and you can detect some topological properties of the knot by measuring its magnetic field. So using the Yang-Mills equations, you can actually explore much more subtle behavior, much more subtle properties of the knot. You can distinguish very complicated knots from each other because the space of solutions to the Yang-Mills equations is sufficiently different that they can't be the same. And, you know, well, yeah. Stop.
Are we all confused now? No. But you bring up something there, both of you, that you deal with real phenomena. Yours is extremely abstract. We can't see the quarks. We can't see these properties of things. So, and you're dealing with objects or patterns that you can see, but knowing them is another thing altogether. So you penetrate with the mathematics. I wonder how visual you are. Do you visualize, or is this just a bunch of numbers and equations in your head? And those of us who have to visualize are in trouble.
I actually do not visualize very much. I visualize more the relationship between the quantity, the mathematical quantities, than the real phenomenon. I mean, it's I'm a little bit more like this should be bigger than that.
Okay,
and they should go in this direction, not in the, in that kind of relationship.
Okay.
More quantitative than really.
More quantitative.
On the other hand, I visualize everything.
All right, there you are. So is it divided? I mean, are there people that are, or is it in particular?
So.
Yes.
I think so.
Yeah, there's different mathmaticians have different, just like people.
Right, exactly. Strategies,
skills,
there, but it comes out how they think, and it's quite. You hear it in physics too. The way that people think, it really varies quite a lot. There's not one size fits all by any means. So I'm running out of time, regrettably. Like there are about 10 more things to ask you. I know that you will come back soon, and we'll have version 2 here, but I need to let the audience talk to you a little bit, and I will thank you both very much, and then turn it over to you folks to take care of questions in our remaining time. Thank you very much for joining us. And now it's your turn, and I'm going to get out of the way here.
My students, 8th grade and under, are absolutely fascinated now with the spirals in nature, and would love to know your mathematical approaches to spirals. If you could come to meet with them, how would you, what examples of nature would you draw on, and so forth? Obviously there's Nautilus, but for mathematics.
Well, there's the seeds in a sunflower, that if you look at how they originate from the central seed, they actually it's a spiral. But if you count them, the number tends to be very close to the Fibonacci numbers.
Like the Nautilus.
Like the Nautilus.
But what about the double spiral and the pine cone?
Yeah.
Well, that's another great example.
But I think nature just always optimizes. So that's usually is the configuration of some optimization problem. And we can see, in math, in abstract sense, we want to optimize the best way to do a certain thing, then we come up with shapes that are like that as well. Nature just does it on its own. So.
You mentioned a couple of times in this discussion about examples where research in pure mathematics some of the centuries ago just yielded no obvious application, therefore the term pure mathematics, I guess. And until a certain amount of time went by, in some cases a century or more, I guess complex numbers would be another example. I was just wondering if either of you would be willing to speculate on one or two examples of research in pure mathematics now where there's just no possible application, even in theoretical physics, but you have a hunch that in a century or two, all of a sudden.
Good question.
Gosh, that's
it's a
it's a toughie. Yeah. Well, in some sense, I think most of what happens in mathematics will have applications. I mean, it's just, I think that in a sense, the most interesting application is this idea of applying number theory to coding, because that's sort of, it's only because that number theory problem is one that's, on the one hand, you can compute because you're just dealing with numbers, it's phrased in that way, and on the other hand, it happens to be really hard to compute. So that's why it was useful in coding theory, because to crack the code, you have to do some horrendous computation. So that's what makes it so hard to predict, because why mathematicians were exploring finding these harder and harder problems just because they want to solve harder and harder problems, and it just happened that that was useful. So I can't actually answer your question.
No, but I also, my point of view on this is that new mathematics somehow is generated all the time, but there are people that are working in different branches of science that now are very aware of what's going on in math. Yeah. So the use is much more direct and much quicker. While before it took like 100 years to do this, now it's sort of like people hear about this and then they understand, oh, I can use it for this machinery to work. So I feel like really the time is much more short, the interval time between the very new fact and the application for it. So for example, there were some math that was used in order to understand the flight of flocks of birds. So why do they fish? Why do they do that? And so then applied mathematicians start looking into that kind of mathematics and apply it to, for example, to understand or to study where in big cities like Los Angeles there are more crimes happening, and try to predict that by using the kind of interaction that happens with the birds and apply it to what happens when there are drug-related crimes and things like that, and try to allocate police people in certain neighborhoods and know more about other neighbors because they kind of predict that there's going to be more need than others. So this is some application that just happened recently because people just make a lot of connection much faster now, I think.
You mentioned that you've observed the time you've been at MIT, the way the students' level has improved. Now, I would assume that the percentage of foreign students has increased dramatically. I wondered whether you think that.
I don't think so. Actually, I mean, when I say that, I just compare. The ones that it's easiest for me to compare with are the ones like me, the ones who are trained in the
He
US.
went to MIT.
I went to MIT as an undergraduate, but I went through high school in suburb of Buffalo, and these kids just know a lot more than I did, and they have much better study skills than I did. I mean,
but where are they coming from?
Yeah, that's the question, though.
Well, I don't know what. What
I teach at Northeastern, and uniformly, the really solid students, the ones who do their homework, the ones who are really very much at the top of the class, are the ones who come from Southeast Asia, for example, or Pacific.
I mean, I think at MIT that's not so true. Yeah. I mean, there certainly are, fantastic students who, at least have some roots that are not in the United States.
But they all come from schools where, at least at MIT, they are all interested in science, and they all have really done either math or other kind of science really at a high level before they come there. Yeah. In fact, recently, more than the last couple of years, more than before, a lot of them place out 1801, which is the regular calculus class. They start immediately with multivariable calculus, or even skip that and start immediately with ODE. I mean, this is how, I mean, it's kind of, we see that because we teach these classes, and over the year they shrunk, like the beginning one shrinking, the other one. And so, but they receive an education that is certainly made better by either the help of the family or because the high school where they went is a special high school that specializes in science, or, I mean, it's not the average. Yeah. Obviously.
And, you know, also, I mean, one thing that might be, this might be a symptom of is just simply that, you know, we're at the end of the baby boom kid generation. So these are, you know, right now, you know, the selectivity of college admissions is extremely high. 9%. I mean, 9% at MIT. And that has a lot to do, you know, of course it's easier to apply, so there's probably more applications, but it's just the pool of students is huge right now, and it's probably going to decrease, and it'll be interesting to see if, you know, we're picking 1,000 students out of, you know, this, you know, the size of the student body is constant, the pool is increasing, so I hope the student body is better, and it certainly is, but we'll see if it tails off.
That's very interesting. So we have to stop recording, but I think they can stay a few more minutes if you'd like to talk with them.